Okay, so we're going to do just one quick lecture on mechanisms and Kurodara mechanisms, and we just do a couple of examples. So let's start off, for example, with this reaction. And the question is, draw a reasonable Kurodara mechanism to account for the following transformation. Let's make this HCl gas. And you end up with 1, 2, 3, 4, 5 Cl. Okay. So I look at this and I say, well, what are we doing? And the answer is, well, we have taken a ring, a cyclic species, and made something acyclic. And I have to identify pieces of my starting material in the product. So if I take my O as a marker, right, I've got an O here and I've got an O here. So clearly this O is that one because there's no oxygen in my reagents. And I'm going to say, well, the O is bound to one methylene, which is bound to another and another and another and another. So in fact, there are actually 1, 2, 3, 4, 5 methylene groups in my substrate. And sure enough, there are 1, 2, 3, 4, 5 methylenes in my product. So I can say this O, right, is bound to methylene, 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 methylene. Or if you want, the O is bound to methylene, 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 methylene. So in a sense then, this Cl, which is bound to methylene group, is going to be bound to probably this methylene or maybe even this one, okay? Well, I also know, so I have a sense of what's happening, right? In this reaction, clearly I am breaking an CO bond. I'm also breaking an HCl bond. I am making a carbon-chlorine bond. And I'm also making an OH bond, right? I'm also making an OH bond, okay? So I've got a sense of the many things that I'm doing. Well, I know that HCl is an acid. Acids do one thing and one thing only. They protonate. And proton transfer is the fastest and therefore the first reaction in organic chemistry. So if HCl is being used, then I know that the HCl is protonating somebody. And the question is, who is HCl protonating? And the answer is the base in the molecule. And what makes me basic? What makes us basic? It having either a lone pair of electrons or a pi pair. So I can say then that the first step of my mechanism is that the lone pair of electrons in the O is attacking the HCl, and the HCl bond breaks. That is an acid-base reaction, so it's an equilibrium. I'm going to lose chloride, and I will generate this species. Okay, this is called an oxonium ion. Right, this is an oxonium ion. Well, so I've actually done 2 of the 4 things in my laundry list. I have made the OH bond. I have broken the HCl bond. What I need to do next is to break this carbon-carbon bond, right? This carbon-oxygen bond. And I also need to make a carbon-chlorine bond. I need to make the carbon-chlorine bond. Well, I can easily imagine that the Cl minus, which we already said, has to bond to this carbon or that one. That with my methylene sequence would be correct. The Cl minus is nucleophilic. And I can easily make a case for the Cl minus attacking this carbon because, for heaven's sake, the carbon is bound to O, which is ordinarily electronegative. But it's actually now bound to O plus, which makes the O very electronegative. And that puts a significant positive dipole on both this carbon and its cousin, that carbon. So if the chloride attacks this carbon already has an octet. There are 2 H's that I'm showing, and that's 4 electrons, and 2 here and 2 here. If it attacks the carbon, the carbon has no choice but to relinquish its hold on 2 more electrons. And what will it do? It will dump the electrons onto the O plus, which has been sucking them anyway, and that's going to give us our product. So we end up with this species, which I'll draw this way, right? I'm going to draw it like this, right? Which is the same as that one, okay? So I have Cl attached to methylene, 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 OH, Cl attached to 1, 2, 3, 4, 5 methylenes and an OH, okay? So that would be a reasonable Kurodara mechanism for that reaction. What about if we tried, let's say, let's do this one. So let's take a ketone and treat it first with, say, ethyl lithium, followed by ethyl bromide or something. And that's going to give rise to this compound. Okay, so I'm treating this ketone with ethyl lithium followed by ethyl bromide, and I make this species, okay, which is, let's see, 1, 2, 3, 4. So it's 2-ethoxy, 2-methyl butane. Okay, so it's 2-ethoxy, 2-methyl butane. So how do we do that reaction? Well, I know that ET bound to lithium is really going to be ET minus for all intents and purposes, because the lithium is electropositive, and so it's actively going to be dumping electron density onto the carbon, which makes the carbon very, very negative, and therefore the carbon is going to be a very potent nucleophile or base. So I have to figure out what role is the carbon playing. Is it a nucleophile or is it a base? Now, if it's a nucleophile, we talked about that in class today. If I have hydroxide, right, attacking, say, this compound, if the hydroxide gets incorporated into the molecule, it's acting as a nucleophile, right, OH minus as nucleophile. On the other hand, if the hydroxide is not incorporated in the molecule and I end up with a pi bond, then hydroxide is functioning as a base. So on the one hand, it's attacking this carbon and I'm losing the bromide. On the other hand, it's pulling off a proton, right? On the other hand, it's pulling off a proton, right? And we're making the corresponding alkene. So if my electron-rich species is incorporated into the product, it's acting as a nucleophile. If it is not, it is acting as a base. And I'll know that because when it's acting as a base, it's going to do an elimination reaction, right? This is E, this is SN. And in an E reaction, I'm going to make a pi bond where there was not one. So ET minus is electron-rich, right? ET minus is electron-rich. So you can either function as a nucleophile or as a base. So which one is it? Well, if it were a base, I'd pull off a proton, right? The ethyl would not be incorporated, and I'd end up with a pi bond where I didn't have one. Well, I've got a C double bond O here, and there's no pi bond whatsoever in this molecule. So this could not be functioning as a base, right? Because if it were, I'd make a pi bond, and the other thing is, clearly the ethyl group is incorporated into the product. Because if I look in this substrate, I have a 3-carbon species. One, I've got a methyl, a carbonyl carbon, and a methyl. Well, if I look at my product, I've got methyl, carbon bound to O, and a methyl. So methyl, carbon bound to O, methyl. Methyl, carbon bound to O, and a methyl. So clearly, this portion of the molecule is from my substrate. And what I've done is I've put on an ethyl group on the carbon and an ethyl group on the O. That's functionally what I've done. So clearly, it means this ethyl gets incorporated, this ethyl gets incorporated. So as our discussion, this ethyl must be functioning as a nucleophile. 1, because it's incorporated in the product. 2, because it's not acting as a base because I'm not making a pi bond in the molecule. Okay, so it's really important that we have a sense of what's happened in a reaction. Basically, where have our pieces gone? And I've identified that, my pieces, I can find my methyl groups and my carbonyl carbon. All right, so functionally then, this ethyl is acting as a nucleophile. So I'm going to redraw it and say, well, the ethyl uses the electron pair in the carbon-carbon bond and attacks the carbonyl carbon. And of course it does, because the carbonyl is the only electrophilic site in the molecule. So let's think about it. In a carbonyl group, I have the inductive effect of the O, which draws electrons from the carbonyl carbon. And I also have the companion resonance effect, right, in which I can actually draw a positive charge on the carbon and a negative charge on the O. So the combination of induction and resonance makes this carbon very, very delta positive. So it's not surprising then that the electron-rich ethyl minus can attack the carbonyl carbon. Now when it does, obviously we're going to break a bond. And the question is, which bond do we break? And the answer is the labile bond. So the labile bond will be the pi bond. Okay? So I'm going to erase, well, let's just go down here. Right? So if I break the pi bond, right, if my Et minus, my ethyl lithium, attacks the carbonyl, right, what I'm going to get is bang, bang. So let's do this one. And I'll have O minus and my ethyl group. So the ethyl group gets attached to this carbon, right? My double bond O becomes a single bond O minus. And I'm going to end up losing lithium plus, and the lithium plus will just associate itself with the minus charge as just a balanced charge. In the second step, I feed this compound ethyl bromide. Well, this is now a nucleophile, right? Or it's electron rich, so it can either be a nucleophile or a base. And if I look at my product, right, if I look at my substrate, ethyl bromide is this molecule. Now, if the O minus were acting as a base, it would pull off the proton and I get a carbon-carbon double bond, right? If it's acting as a nucleophile and the O gets incorporated into the product. Well, that's what I did. So the O minus then must be attacking the ethyl. I'll kick out the bromide, and we'll end up with our product, which is this compound, right? O ethyl, and then my ethyl group, which is the product of the reaction. So what we did is the nucleophilic attack by ethyl lithium on the carbonyl. Cleavage of the pi bond gives rise to the tetrahedral intermediate. It's called a tetrahedral intermediate, which is typical of nucleophilic attack on the carbonyl. Then the intermediate attacks the ethyl bromide, kicks off bromide. We have to make sure we have mass balance, and we end up with our product. Now, obviously, the lithium plus gets associated with the bromide, and my inorganic product will be lithium bromide, okay, which will crystallize out of the solution. Let's do another one. Let's do a, let's see, let's do this one. Let's see. So let's treat this compound with let's say, right? And let's try it with hydroxide, followed by, let's say, cyclohexyl bromide. And my product is going to be this one. Okay, so we're going to draw a curved arrow mechanism for that reaction. This looks funny. So we're going to draw a curved arrow mechanism for this reaction. So let's get a sense of what's happening here. So I've got carbon 1, 2, 3, 4, 5. And I'm going to use my carbonyl as a marker, because I've got a carbonyl here and I've got a carbonyl in the product. So let's make this carbon number 3. So I can easily see, well, maybe this is N1, 2, and this is 4 and 5. So I know where my carbons are, and clearly the 6-membered ring is coming from the cyclohexyl bromide, the bromocyclohexane. Okay, so I have a sense of who's going where. Again, we have hydroxide. Now, hydroxide can function as either a base or a nucleophile. Which role is it playing? Well, if I look at my product, there's no hydroxide here. Further, whereas I only have one carbon-oxygen double bond in my solid material, I still have one, which means I haven't made a new pi bond, which means I'm not eliminating. So since the hydroxide is not incorporated in my product, it's not acting as a nucleophile. So what do I have to do? Well, if carbon number 4 has the cyclohexyl group on it, if I look, this carbon has one H. If I look at my solid material, this carbon has two H's. So the hydroxide must be pulling off an H. So I'm going to say step 1 is going to involve the hydroxide pulling off an H from carbon number 4. So let's have hydroxide act as a base, deprotonate the H. That's an acid-base reaction. I'm going to lose water, and that's going to give rise to my initial species, which will look like that. I have to express concern because I'm going from O minus to C minus, and C minus is a stronger base than O minus, except for the fact that this species, in fact, is resonance stabilized, and resonance stabilization is really quite potent. But if you look at the resonance form, in it, I actually have the minus charge delocalized over an O minus as well. So it's delocalized over OCC. So this is clearly then a more stable conjugate base, a more stable base than this is, because here the minus charge, all this on an O, is stuck on the O. Whereas this minus charge is on the O, and it's also being shared by the carbon. Okay, so this is going to be a more stable species, aka a weaker base, and the strong base therefore gives rise to the weaker base. So that entity, right, is my first intermediate. Then I feed it cyclohexyl bromide, right, or bromocyclohexane. And it's not surprising, this is going to act as a nucleophile, attack this carbon, the bromide gets kicked off, and I make my product, right, and I lose Br minus, right, in the steps. I maintain my atom balance. Okay, let's do one more, and let's try this reaction. If I treat this compound with H3O plus, what I end up with is this compound. Okay, so let's write a curved arrow mechanism for that reaction. Well, again, we've got to have a sense of what's going on in the reaction. And it's really important, guys, when you're doing mechanism, or when you're doing, as we see later on, conversions, or really, quite frankly, any organic question. It is really important that you interrogate the question. I'm going to write that down and then erase it. It's really important that you interrogate the question. Okay, that's a really important feature to analyze any situation. You have to ask yourself, what information is the question giving you? The question comes with built-in information. You must seek it out, okay, by interrogating the question. So, for example, I would say, look, I've got an acid. Acids do one thing and one thing only. They protonate. Proton transfer is the fastest, therefore the first reaction in organic chemistry. So I know step 1. Now, the acid is going to protonate anybody with a lone pair or a pi pair. And it so happens I've got two O's in a molecule, and they're actually equivalent. So one of the lone pairs on the O's gets involved. And I don't care which lone pair on which O, but I know step 1 is going to be protonation of the O. That's my first bit of interrogation. Let's figure out what's happened. Well, you know, obviously, I made a 2-carbon product. But I'm starting off with a 4-carbon product, solid material, 1, 2, 3, 4. So I have to interpret then that, look, I must have made 2 of these. So functionally what's happening is I'm splitting the molecule down the middle. Okay? And in essence then, I'm going to take water from the system, and I'm going to have the water bond to my material sort of like this. HOH, HOH. So this O binds to this H, this O to that one, and I make the diol. This O binds to this carbon, this O binds to that carbon, and I make another molecule of the diol. So there are going to be some water molecules involved, and there's going to be some your substrate involved. But basically, one of these will give rise to two of those. So I've interrogated the question, and I kind of have a sense of who is going where, what's happened in the reaction. So let's just go about sort of making it happen, right? We know what sort of has to happen, and let's just make sure that those processes are legal. So step one, we've identified as protonation by H3O plus of the ether. And that's going to be an acid-base reaction. I'm going to lose water. And I'm going to make this species. Okay, OH plus. Okay, well, so what I've done here is I've made my first OH bond. Well, clearly, remember we said at some point we need to get an OH to attack these carbons. Why would OH, where would the O come from? The answer is from water, which is present in great abundance. And it's right for the water to attack this carbon because this carbon is attached to the world's second most electronegative element, which happens to bear a positive charge. So this carbon is going to be very, very delta positive. So the water attacks, I break the bond, and I'm going to make this species. Now remember we said acid-base reactions are equilibria, as are attacked by water, alcohols, or ethers on a positively charged species. So that's going to give rise to this entity. OH, OH2 plus. And we're all adults. We're in an aqueous medium, so there's water present. Water can function as a base. Pull off the proton, that's an acid-base reaction 2. I'm going to make H3O plus, and that's going to give rise to this species. So we're really getting much closer, right? We're getting much closer. I have made 2 OH groups. So what happens next? Well, whatever I did to the bottom part, right? Protonated the O and had water attack, I'm going to do to the top part. That way I'm going to complete my scission of the molecule. So I'm going to have H3O plus attack, right? Or be attacked, acid-base reaction. I'm going to lose water, and that's going to generate this entity. All right, OH, OH, H plus. And then a water molecule will attack. I'm going to break this bond for exactly the same reasons. That's an equilibrium because we have water attacking something positive. And that's going to give rise to an ethylene glycol. So I'm going to draw the same shape. It's going to give rise to an ethylene glycol. Right, so I'm going to have OH, bang, bang, bang. Right, that's this piece. And it's also going to make OH, 1, 2, 3, 4, OH2 plus. And then a water molecule comes in, acts as a base, sucks off the proton, and gives rise to my second ethylene glycol, and I lose H3O plus. One of the points that I'm going to mention here is that if you notice in this reaction, we used up 1 H3O plus and 2 H3O pluses. But we generate 1 H3O plus, 2 H3O pluses. So the H3O plus really then is simply a catalyst, right? It's regenerated at the end, and it makes the reaction easier because instead of having water attack this carbon, which of course it would not do, we have water attack the carbon bound to the O. Let me just sort of highlight that point a bit, right? It's illegal for a water molecule to attack this carbon as written, because if it does, I'm going to generate this entity, right? I'll generate this entity. So I would have made from water a weak base, O minus, which is a stronger base. Okay, and that's illegal. Now, as it turns out, if I left this compound in water for 10 years, it will eventually undergo what's called hydrolysis, which is cleavage using water. But what would happen is it would hydrogen bond to a water molecule. And in the hydrogen bonding, what you actually do is you bleed electrons from the O, which bleed electrons from the carbon, and so the carbon actually ends up being a lot more delta positive. So when the water attacks it, what you actually end up doing is you generate not an O minus per se, but the OH. And this OH minus, that minus charge is not going to be stuck on the O. It actually be hydrogen bonded away by, you know, a bunch of water molecules in the system. Okay? But in the reaction shown here, instead of having the water attack a carbon attached to only O, so you're going to end up making O minus at some point, here the water attacks a carbon bound to O plus. And so I never end up making O minus. And so this reaction becomes more feasible. Okay, all right, so we'll stop there. I'm hoping that's enough mechanisms. I think we did 3 or 4. 1, 2, 3, 4. Okay, so I'm hoping that's enough of enough extra material that you guys would have a bit more comfort with curved arrows. All right, thank you guys. Good luck.